By 2026, the price of lithium carbonate had fallen by more than 60% from its 2022 peak, pushing the cost of LFP batteries down to just 60 to 70 US dollars per kilowatt hour at the pack level. Yet the paradox is this: global automakers continue to pour billions of dollars into the search for a battery cheaper than lithium. Sodium-ion batteries are marketed as being 20 to 30% lower in cost.
My name is Tom
while
Stepien,
solid-state
CEO of
batteries are
Amprius
praised for reaching
Technologies.
400
Amprius
to
is a
500
U.S.
watt-hours per
lithium-ion
kilogram
battery
and charging in
manufacturer.
minutes.
It is
But if these
specialized
numbers
in that
were
it has
truly
a
good
silicon
enough,
anode.
why by 2026
We have about 20 different
has
battery
not a
types.
single major
They
automaker
offer
chosen sodium-ion
really
or solid-state
high
batteries
energy
as the core
density
platform
that
for
allows our
mass-market electric
customers to
vehicles?
have crafts,
The answer does not lie
drones,
in media
motorcycles
narratives,
that
but in
are
technical
lighter,
limits that
longer,
engineers
and
simply
stronger.
cannot avoid.
One of the many things that
In theory,
happens at CES
sodium-ion
is that
batteries
they
appear highly
recognize
compelling.
innovators
Sodium is cheap,
around the world.
abundant,
There were
and far less
4,000 companies
exposed
that
to
applied for
geopolitical
an
risk.
innovation award,
But
and
energy
Amprius is
density
one of those.
is where the story
It's
begins to fall apart.
a testament to the
best
hard work
commercial
that everyone
sodium-ion
inside of
cells
Amprius has
available
been
today
doing,
from
and the
manufacturers
customers
such
who
as
recognize
or
what we have and the
reach
growth
only
that we've
around
enjoyed.
140 to 160 watt-hours per kilogram. By comparison, mass-market LFP batteries already operate in the 180 to 200 watt-hours per kilogram range, while premium NMC chemistries easily exceed 300 watt-hours per kilogram. This gap is not academic. It is brutally practical. To deliver the same usable capacity of 75 kilowatt-hours, a sodium-ion battery pack would weigh roughly 150 kilograms more than a lithium-based pack. That excess mass does not merely reduce efficiency. It forces compromises across the entire vehicle: suspension tuning, braking capacity, tire wear, crash dynamics, and structural reinforcement. Any savings of a few $100s at the battery level quickly become meaningless when the rest of the vehicle has to carry the penalty. This is precisely why sodium-ion has not replaced lithium, despite years of promotion. It is not because engineers dislike sodium, but because energy density dictates everything that follows in vehicle design. Have you ever wondered why it took us 30 years to optimize lithium batteries, yet we expect sodium to succeed in just a few years? The answer lies in the fundamental nature of the periodic table. Sodium ions, radius 1.02, are about 34% larger than lithium ions, 0.76. When these oversized ions repeatedly move in and out of the hard carbon anode structure during charge and discharge, they cause severe volumetric expansion. This repeated expansion generates enormous mechanical stress inside the cell, leading to microcracks, loss of electrical contact, and rapid capacity degradation. As a result, today's commercial sodium-ion batteries typically achieve only around 2,000 to 3,000 charge cycles, while modern LFP batteries have already comfortably reached the 6,000 cycle threshold. For an automaker that must guarantee an 8-year or 160,000 kilometer warranty, using a battery chemistry with less than 50% of the mechanical durability represents an unacceptable brand risk, no matter how cheap the raw materials may be. If I told you that sodium-ion batteries are currently more expensive than lithium batteries in practice, would you believe it? This is a reality often hidden in financial reports. It is true that sodium carbonate costs only about 200 to 400 US dollars per ton, dramatically cheaper than lithium carbonate at 15,000 to 20,000 US dollars per ton. However, raw material costs, BOM, account for only about 30% of the total cost of a battery cell. The remaining 70% lies in manufacturing processes, yield rates, and supply chain scale. LFP batteries have benefited from massive economies of scale, driving costs down to extremely low levels, around 60 to 70 US dollars per kilowatt hour at the pack level. By contrast, due to low production volumes and unstandardized processes, sodium-ion batteries are still struggling at around 80 to 100 US dollars per kilowatt hour. To fully transition to sodium, automakers would have to rebuild production lines and accept risks from new suppliers. Until sodium-ion truly breaks the golden $40 per kilowatt-hour threshold, which experts predict may not happen until after 2028, it remains a promising but impractical niche technology. While the world is still debating sodium, giants like Toyota, Samsung SDI, and QuantumScape are quietly preparing a dramatic upheaval with solid-state batteries. According to recently updated mass production roadmaps, the next 3 months, Q1 2026, will be a pivotal moment as gigawatt-hour scale pilot lines officially begin operating to produce cylindrical solid-state cells. The choice of a cylindrical design instead of pouch cells is a masterful engineering decision. The cylindrical form can withstand extremely high external pressure, a mandatory condition for maintaining stable contact between the solid ceramic electrolyte and the electrodes, thereby preventing the formation of dendrites, salt crystals that cause short circuits. The industry's goal over the next 90 days is to reach an energy density of 450 to 500 watt-hours per kilogram, roughly 3 times that of current sodium-ion batteries. This is precisely why premium automakers would rather wait for solid-state technology than rush into sodium. If solid-state batteries are so powerful, why don't we see them in every vehicle yet? Automakers are not tech startups. They are organizations with an extreme focus on risk management. Solid-state battery production requires specialized equipment, such as hot isostatic presses, costing tens of millions of dollars, operating in ultra-dry environments with humidity below 0.1%. A single microscopic dust particle or a tiny defect in the ceramic layer can destroy an entire cell. Moreover, we still lack real-world degradation data over a 10-year period. How can a rigid ceramic block withstand continuous highway vibrations, temperature swings from minus 30 degrees Celsius to 50 degrees Celsius, and mechanical impacts without cracking? Automakers cannot afford to learn by paying the price on millions of customers. That is why, in the upcoming 3-month plan, solid-state cells will only be deployed in limited A-sample test fleets to collect real-world operational data rather than being sold at scale. So what is the ultimate truth? The future of the EV industry will not be dominated by a single battery chemistry, but by strategic layering based on real-world needs. Sodium-ion batteries will find their sanctuary in ultra-cheap city cars under $10,000, where users only need 100 to 150 kilometers of range and regularly charge slowly overnight. Meanwhile, LFP batteries will continue to be the workhorse of the mass market segment thanks to their perfect balance between cost and durability. And finally, cylindrical solid-state batteries will become the symbol of luxury and performance, reserved for flagship vehicles capable of charging fully in 10 minutes and crossing continents.